So our next speaker is Gordon Osinski. His title is Robotic Precursor Assistant and PostCursor Activities in Support of Human Lunar Exploration, Lessons Learned from Analog Missions. So take it away.
All right, thank you. And it's a pleasure to be here this morning. I think it's still morning where I am too. This follows on nicely from David and Noah's presentation on field geology training. Of course, one of the big things that Noah didn't talk about that has changed since Apollo is how far technology has come. And so essentially the take-home message, if I run out of time at the end, is that my view, and I think we can support this with lessons learned from Apollo missions, is that we should be sending robots in advance. We should be working with rovers while they're humans on the moon and leaving the robots behind to do post-cursor activities. I would like to thank all the co-authors on the actual presentation here. And also, if I can get the slide to move on, a whole number of other participants, well over 100 people who have participated in the various analog missions that I'll be talking about. So thank you to all of those who are staffing mission control and doing field support. So I'd love the opportunity to talk about, all of the analog missions that we've been leading here at the University of Western Ontario in London. But I'm going to focus on what I think is the most relevant one here today and for this audience. All of these in one way or another have been funded by the Canadian Space Agency. So thank you to them for having the foresight to fund these analog activities. And so today I'd like to take myself back actually, and you back about a decade when we carried out over 2 years robotic precursor and post-cursor analog missions at the Mestastin Lake impact structure in Labrador. So these were a series of lunar analog missions in support of human sample return. So that was the focus. The scenario was that in 2010, we had a robotic precursor mission carried out over about a month. And then in 2011, we went in with the simulated astronauts and also carried out some post-cursor activities. You can see the science questions that we went in with in the bottom left. We had a remote mission control. So this was a fully simulated end-to-end mission. We had the mission control located here in London, Ontario. To follow on from David's talk, and Noah's as well, heavily impacted terrains is what we're going to be looking at on the moon. The Mestastin Lake impact structure in Canada, I would argue, is one of the best, if not the best, scientific analog for lunar craters. It's a complex impact crater, about 28 kilometers across, and the main target rock is a northocite, so it's an excellent lunar highland analog. We have a central uplift that you can see in the middle of the lake. Yes, there is a lake, not a fantastic lunar analog, but it also provides some challenges for navigation. But we have a northocite in the form of shocked rocks. We have impact ejecta preserved. We have impact melt generated from a northocite precursor. So it's a really excellent analog, pretty remote, and still a lot of science to be done there, which means we can have science-driven analog activities. So jumping into the results, precursor data, what was the value? Basically, the bottom line is that of all the data sets we collected during the precursor missions, handheld spectrometer data, geophysics data, it was really the high resolution panoramic imagery and LiDAR data that proved most useful for the follow-on missions. It helped in terrain orientation, but it really helped in traverse planning for the human missions in the following year. And so what we have here is a quick bird image that we essentially, decrease the resolution to match what we have the highest resolution of for the moon. And, you can see some features. Hope you can see my mouse. I know it doesn't come over too well in Zoom. There's some perhaps faint layering. If you can, pick this out, there's a brighter outcrop here. But if I zoom into a LiDAR image, this actual hill here is called Discovery Hill. It's in some of Richard Greaves' earliest papers, and it's one of the most spectacular occurrences of columnar jointed impact melt in the world in an impact crater. So this is about a 100-meter high cliff of impact melt that you really have a hard time seeing in this, top-down satellite image. If we move on again, this is some high-resolution panoramic images showing this outcrop. And so, this enabled the team, both in real time during the precursor missions, but also afterwards, to come up with a whole bunch of hypotheses about what they were seeing based on this on-the-ground imagery. I'm not going to delve into it too much today, but of course LiDAR is again something that we've been working on here quite a bit, and it also is suitable for addressing some of the illumination issues on the moon. And just to quickly go backwards here, this type of data set, this could have been completely in shadow, even on the ground. And so LiDAR data is definitely something that I would argue should be on future robotic precursor missions. Moving into assistance, so this is something I think a lot of us have thought about. I am a field geologist by background and training. At first glance, it's like, oh, I don't want any robots with me, taking my time away. But we did kind of look at, and I have a few stats to share with you. So, having a robot in the field with you does take some of your time away as a human from your activities. And, some of the percentage here is about 13% of the time during this EVA was spent on working with the rover, in this case, actually driving the rover, teaching it some paths. But we gained an additional 546 minutes of robotic operations during that same EVA. And then I'll get onto the next slide. That doesn't even include the value of the post-cursor activities. And in particular, having the rover there with the humans, it's a lot easier for rover navigation. You can teach the rover some paths that it can then drive back autonomously afterwards. So essentially there was, greater science return. This is something that I think, this was something that we looked at very briefly, during this one Analogue mission, and I think it does deserve to be looked at in the future, is how to really optimize the robotic human interactions in the field. Moving on to post-cursor work, huge benefits, multiple things. First, in being able to revisit, we were only able to do it over days, but even that was valuable. But imagine having a rover there at the same site, weeks and months, you're starting to analyze the samples that we've brought back. You've got more questions, more hypotheses to be tested, so the rover can go back to previously visited sites. But it also then enables the rover to extend, go into previous sites that were not able to be visited by the humans. And the teach and repeat functionality that we have in robotics now is quite new a decade ago. It's fairly commonplace now. Essentially, once a rover is driven the path once, it can basically do it on its own without GPS. Again, really optimizing and increasing the value. And I think I see you popping up, Sherry. That is my last slide, and hopefully there's a minute or two for questions. Thank you.
Thank you, Oz. That was perfect timing. And we do have a couple minutes for questions if anyone wants to type in the chat.
So I know there's some chat messages for previous speakers too, but
yes.
questions if we got time.
All right. Well, Oz, I have a question for you. So, you talked about wanting to do more of human-based field operations rather than take, it's a lot of time to use a robot. Were there certain things that you really enjoyed about working with the robotic operations that you felt are going to be really useful?
Yeah. I do think, optimizing, this is where, I think the mission control architecture for this that, we had fairly simply back then will be very important. Do you need a parallel, how do you structure that, right? Is it the same science background controlling and directing the rover while the human astronaut is there in the field? What do you do when the astronaut was sleeping, which is not something we tested at Mistastin because it was dark. But, we're looking at, going back to one of Noah's points, going back to high Arctic analog sites here in Canada, where we can do 24/7 operations, and really thinking about, because let's say we got 6 hours of EVA, what we didn't do, what do you do overnight with that robot while the humans are sleeping? And so I think a lot of the emphasis is going to be on figuring out how we structure the mission control and the science backroom here on Earth to really optimize all of that. And the best way to do that is to go out and do it here on Earth.
That's great. Thank you. And we had a couple questions coming in that I think will be a great jump off for our discussions later on. So we'll save those.
Sounds good.
And thank you.